What is a force? A force causes motion. A force can have different strengths. Forces can have different directions. These combined make vectors perfect for representing forces. We can consider a space where every point has an assigned force. An object in the field will have a force applied to it by the field. We can measure the arrows per area to gauge the strength of a field. As you can see, the field is stronger at the bottom right than at the top left. Isaac Newton introduced the concept of forces and everything that comes with it. But it was Lagrange and Hamilton who reformulated mechanics in terms of energy changes. These theories describe the same universe but in different ways. This suggests that energy and forces are deeply connected, which makes sense since forces cause motion, and motion is a transfer between energy stores. Consider an apple falling. We can track its potential and kinetic energies over time. These quantities are opposites. The sum of kinetic and potential energy is constant in the systems we will be considering. We can then derive a relationship between the change in kinetic energy and the change in potential energy. If we go back to the apple, we can derive an equation for its velocity. Using energy made this calculation very easy. If we tried to do the same thing with forces, it would be much more challenging. Let's consider applying a force to this car. The car will move over a distance due to this force. We can consider how this force varies with distance. This will result in a graph. Note that the area under the graph gives us the work done by the force. Sometimes the force can vary. Since the work done is the area under the curve, it can be given by an integral. This assumes that the force always acts collinearly with the displacement. There are more complicated definitions of work which we won't get into today. When the force is opposite to the displacement, we get negative work. This just means that the work was done against gravity. By considering how the changes in work and potential energy relate, we can show that the change in work is the negative of the change in potential energy. This only works because our force is opposite to displacement. By considering the change in kinetic energy in this situation, we can see that the change in work is equal to the change in kinetic energy. As the apple falls, it speeds up and gains kinetic energy. The work done is positive, and the change in potential energy is negative. If the apple is lifted, the scenario is the direct opposite. However, we can consider the apple's perspective as well. If the apple falls, the field's work is positive and the apple's work is negative. If the apple rises, the field's work is negative, but the apple's work is positive. We therefore get the following relationships between the change in potential energy and the work done from different perspectives. Note that the work done by the apple is the perspective considered in the A-level specification, but the work done by the field is generally used more often. This will cause confusion if not handled carefully. In this video, we will use the work done by the field. Potential is defined as the potential energy per unit. For gravity, this would be per unit mass. Using this, we get that the potential in a uniform gravitational field is just negative g times x. An equipotential is the path taken that causes no change in the potential. In other words, the rate of change of potential with respect to displacement is zero. For uniform fields, it's easy to understand that an equipotential is a straight horizontal line. But we can do some maths to verify this is indeed true. If we take the equations we've considered so far, we can derive a very important relationship between potential and field strength. Note that we can convert the change equation into a differential equation, and we can also get a differential equation for force, using the chain rule to arrive at a crucial equation. We can see that the gradient is the negative rate of change of potential with respect to displacement. Note that for A-level physics, the difference equation is sufficient. A uniform field is one where the force is the same everywhere. For the uniform gravitational field, the force at each point is equal to mass times g, and the field strength is 9.81 newtons per kilogram. When an object moves in the field, the work done is the product of force and distance. We can see that our integral formula gives us the same result. We can count the lines in an area to find the field strength. As we move the area, we can see that the field strength decreases. Newton's law of gravity perfectly captures this relationship. Note that the forces equal and opposite. Because the Earth is so much larger, the gravitational force it experiences from the apple has negligible effect on it. As the distance increases, the force decreases. We can also derive the equation for the field strength, which also decreases with distance. We can track the force due to gravity when the field acts on the apple. Note that we are measuring distances from the center of the Earth, and for this reason, the gravitational force is always negative since it points toward the Earth. The area under the force graph will be the work done by the field. We can get a formula for the work done on an object by considering the field bringing it from infinity to a distance r. By working out the integral, we get that the work done by gravity is capital G times capital M times little m over r. While the field did positive work in bringing the apple to r, the apple did negative work. By considering the area between two distances, we can get that the integral gives the change in work. If we consider the apple being pulled by the Earth, the work done by gravity is positive, and the work done by the apple is negative. The integrals confirm this. In the opposite case, where the apple is moving away from the Earth, the work done by the field is negative, and the work done by the apple is positive. In general, the formula for the change in work done by the field is as follows. Since the change in work done is the negative change in potential energy, we can find the change in potential. We can use the relationship between potential energy and potential to derive a formula for the change in potential. As we let R1 go to infinity and R2 go to R, we can get the formula for the potential. Note the following relationships between work done and potential. In A-level physics, the work done is assumed to be by the apple. We can now think about equipotentials. By solving the differential equations, we get that an equipotential is a path with a constant radius. The equipotentials are therefore just orbital paths. Note that along an equipotential, no work is done. Since no work is done when you travel perpendicularly to the force, any equipotential is just a path that is perpendicular to the force at each point. These are the equipotentials of uniform and radial fields. Note that they are always perpendicular to the field. Throughout this video, we have considered various important concepts related to gravitational fields. If this video helped you understand these concepts, consider liking the video. If there are any specific topics you would like to see in the future, comment below.